initiating this session 6A in Telecommunications Engineering, room A. As I told you before, we have around 15 minutes for each presentation, but I will ask you to use around 12 minutes, so we have a few minutes for questions, okay? So the first presentation is going to be held by Muhammad Ali from Turkey, and the title of the presentation is Improved Hybrid Precoder Design for Secure mmWave MIMO Communications. So Muhammad, when you want.
Thank you very much. Thanks for a nice introduction. This is my outline. Let's start with the current issues. Basically, with the passage of time from last few decades, the demands of mobile users are continuously increasing. Especially, it is foreseen that with the about 1 trillion of connected devices are realized in Internet of Things, for which a huge amount of data rate requirement along with a sufficient bandwidth utilization is required. However, in addition to that, high resolution video applications are also going increase day by day, for which the current spectrum cannot accommodate such huge amount of devices with proper data while providing a proper data rate requirement. So spectrum congestion in current communication system is strongly realized. Therefore, the researchers are continuously striving for the upper part of electromagnetic spectrum that starts from 30 gigahertz to 300 gigahertz, and which are having a very short wavelength in the range of millimeter wave. That's why these are known as millimeter waves. But the problem with millimeter wave has that they have certain degradation issues like rain fading, penetration loss. So the signal may be die out. So therefore, we can also adopt the multiple antenna technology because the shorter wavelength. However, again, the multiple antenna technology has severe problem related to cost and energy consumption, because for every single antenna, a single RF chain is required. And every single RF chain consists of an analog to digital converter, digital to analog converter, and mixer. So it may be very difficult, as well as most important, it will be cost and energy consumption issues. For example, in this specific system, we are using 192 antennas at transmitter, receiver, and eavesdropper side. So it's mean that we required 192 multiplied by 3 RF chains. So this is very unrealistic. So for that reason, the solution is the hybrid beamforming technique. In hybrid beamforming technique, what we are doing, we are basically utilizing a combination of analog and digital precoding. In this way, we are reducing the number of RF chains. So hence we are reducing the cost and energy consumption. Since we also know that the wireless communication has broadcast nature, so that's why the information sent by any user is open, exposed to all the users. So the problem is we have to secure our transmission from the undesired users, generally known as eavesdropper. For this purpose, we need to establish a channel which can enhance the signal toward the desired users and degrade the signal and at the undesired users, known as eavesdroppers. So for that, specifically, we need to improve the signal to noise ratio towards the desired user and minimize the signal leakage toward the eavesdropper side by reducing the SNR signal towards them. But there is also very important thing that if the eavesdropper is equipped with exactly same number of antenna as deployed by the transmitter or the intended receiver, in this case, certain information leakage can be realized. So the main objective of this study is to design such a secure hybrid precoder which can protect the information leakage towards the eavesdropper. And the second objective is that we will compare our proposed model with the most recent algorithm in the literature. In this specific study, we achieved this by applying a famous zero forcing scheme toward the eavesdropper side, which basically suppress the channel, and hence the information leakage can be minimized. And to do so, we are using the physical layer security procedure for specifically targeting massive MIMO millimeter communication systems. So this is our system model. In our system model, we are using a very simple system model in which we have alias, the transmitter, the receiver, Bob, and the eavesdropper. In this case, the transmitter to the receiver channel is known as HP, transmitter to eavesdropper channel is known as HE. In this model, all the three parties consist of the antennas NA, NB, and NE. Here in this model, we will use small a, small b, and small e for the alias, Bob, and eavesdropper. In this model, as you can see that we have digital part and analog part consist of the phase shifters. So basically what we are doing, we are designing a precoder, we are designing a combiner, and a combiner for the Bob, which is intended receiver, and combiner toward the eavesdropper side. However, we will try, it is certain condition. For example, the NS data streams, the expected value of data stream into its transpose will be always equal to this thing. However, it is very important that we should keep our number of RF chain lesser than the number of antennas at transmitter, receiver, and Bob, and this should be greater than the number of data stream. We try to increase the number of data RF chain more than data stream, because for the multiple stream transmission, whereas as I said that number of RF chain should be minimum than number of antenna to avoid the cost and energy consumption issue. So let's start that the signal X is the output of the transmitter, which is alias. So when this signal is received at both sides through the channel HB, we get YB. When this YB signal is processed with the combiner at the receiver side, intended receiver side, we get SB equation. So where in SB equation we have HB. HB is the channel to our transmitter to receiver, and in this equation, the small a with the B and A subscript represent the array response vector at transmitter and the receiver side, whereas this phi and theta are the angle of departure and angle of arrival at the transmitter and receiver side. In similar fashion, for if we are getting SB with the difference that it is subscript with the represent the eavesdropper. As I said that we are using zero forcing technique. In this here, before further analysis, we are applying zero forcing technique on AVE channel using this equation. So this is basically standard performance matrix of secrecy analysis. We are interested is this main equation. The first part, logarithmic part, is the secrecy rate of the Bob, the intended receiver. And the second part is the secrecy rate of the eavesdropper. So basically we are interested in this overall secrecy rate, which is always subtracted from the Bob to eavesdropper, where CB and CE represent the capacity of Bob and Ave. RNB, RNE are the covariance matrices of the Bob and Ave side. So what we need to do, we are interested to get these four terms subject to these conditions: F, analog precoder, digital precoder, analog combiner, and digital combiner. In this equation, two things are very important: this P and this C. These are basically controlling the analog beamformer. Like we can achieve high resolution beamformer by selecting higher value of B. But at the same time, if we increase the number of bits, the circuit complexity is increased. So in this specific study, we are applying low resolution phase shifter and we will use B is equal to 2 value. So first of all, as we know that the channel model that we have selected in this study is sharing scatter model. So in this model, it is millimeter waves. So there will be a certain common angle of arrival and departure between the bob and tape. So what we will try to do, we will first develop a secure channel which is obtained by eliminating common angle of departure from the common angle of departure of bob and F from the bob. So hence we get the secure channel. On this, when after getting secure channel, our accuracy analysis can be interpreted as this equation, similar to the previous one, but we have changed from HB and HE into HS model. However, this is still a complicated hybrid precoder design, because in this model we are dividing our procedure into two steps. First, we are achieving analog precoder and combiner using the conventional method based on this secure channel. However, for the digital precoder and combiner, we are creating the effective channel, which is basically the combination of the obtained analog combiner and analog precoder from the convention method, and then applying SVD operation. From SVD operation, we are getting UR and VR unitary matrix. By exploiting these matrices, we are getting the digital precoder and digital combiner. So at F side, we are utilizing minimum mean square error filter as a average dropper combiner over the effective channel, which is HE into F. Now we are having all the parameters like FA, FD, omega A, omega D, and combiner at the F side. Now we will go to see our simulation parameter. In our simulation studies, we are assuming that our angle of arrival and angle of departure are uniformly distributed between 0 to 2 pi. The covariance matrix we selected is unity for our simplicity. For more comparison, the lower bound we are selecting is specially space precoding, whereas upper bound is generalized eigen decomposition based on full digital precoder with the physical layer security effort. In the following curve, you can see that we are analyzing our analysis in terms of spectral efficiency versus signal to noise ratio. Basically, this blue curve is just our accuracy rate. We are interested in this thing. The black curve representing the bob accuracy rate, the red one average dropper. But we are interested in our accuracy rate of the overall accuracy rate. So you can see that the circle one is representing the most recent algorithm, whereas this square one, the proposed one. You can clearly see that at low SNR value, our proposed model showing similar results. However, at high SNR value, our proposed model showing some better results. In next case, you can see that here we are selecting data stream 4 and number of RF chain is equal to 8. Again, you can see that at low SNR value, our proposed model is representing similar result. However, at high SNR value, our proposed method showing better results. The next final result is the accuracy rate of spectral efficiency versus data streams. As you can see that as number of data streams are increasing, the accuracy rate performance of proposed method is improving. At 1 to 4, the proposed method is slightly improved, but at above than 4 to 8 hour, a slight better improvement can be seen. So the conclusion, in this specific study, we have utilized secure hybrid precoder design for targeting millimeter wave, utilizing massive MIMO systems, and use low resolution phase shifter. To improve from the recent algorithm, we utilize the zero forcing technique at each channel. The simulation studies validated that our proposed method improved the secrecy rate at high SNR value. However, the similar secrecy rate results are seen at low SNR values. Thank you very much. If you have any question.
Okay, thank you very much, Mr. Ali. You got almost in time. So, is there any questions from the audience? Anything from the internet, maybe from YouTube? Okay, nothing also. So I just have a small fast question. I got lost with when you were presenting almost all the distribution, all the evolution of the equations you have to use to find the matrix for the MMS filter. But is this process? I have two fast questions. Is the process adaptive in a way that if the hardware or architecture of the MIMO system changes, is the system adaptive? Can it change in time, or it is fixed for a fixed technology?
Actually, currently we are using a passive eavesdropper. Like in future we can see the active eavesdropper as well. And number two, like in current scenario, you have seen that in our system model we used three basic parameters: transmitter, receiver, and eavesdropper. In future, the number of eavesdropper may be increased. It has the in future they may be active. They may make changes in the real transmission as well. So currently we start from the very simple model. So in this they are passive eavesdropper. They are not active eavesdropper.
Okay, thank you very much. I will say the other question if we have time at the end,
Okay.
just in case, and I will make the next question. So thank you very much, Mohammed. Thank you for your nice presentation. So we go for the next one, which is from Evelina Nikolova. Presentation. The title of the talk is Multiparty Call Control at the Network Edge, presented by Evelina Nikolova Pencheva from Bulgaria. So Evelina, again, you have 13 minutes, and then we save a couple of minutes for questions. Okay, thank you very much.
Thank you. Hello, everybody.
Dear colleagues, my name is Evelina Pencheva, and we are with Technical University of Sofia, Bulgaria. This presentation is on multi-party call control at the network edge. Here is the outline of the presentation. The introduction presents the problem, which is related to open access to multi-party call control using multi-access edge computing technology. Next, the deployment of open access to multi-party call control functions at the edge is discussed. The proposed functionality is illustrated by typical use cases, data model, and interface definition. The service feasibility is illustrated by modeling the multi-party call state as seen by network and application points of view. The assessment of application programming interface performance is done theoretically and by emulation. The conclusion summarizes the contribution. Fifth generation system has huge potential to improve our daily lives in various aspects, including numerous mission-critical and healthcare scenarios. Network programmability is a key feature of fifth-generation system, which, in combination with cloud-based services, can support many use cases, including mission-critical and healthcare communications. Existing research on multi-party call control is focused on third-generation partnership project, mission-critical push-to-talk service architecture and feasibility study. Provisioning of 3GPP mission-critical push-to-talk service relies on deployment of Internet Protocol Multimedia Subsystem, or IMS. In this paper, we study how the open access to multi-party call control can be provided by multi-access edge computing. The research novelty is in delegating the multi-party call control to mobile edge applications deployed in the vicinity of end users. The proposed open access to programmability of multi-party call control does not require deployment of IMS, and thus it reduces the cost and provides the necessary performance and reliability. Distributed core network functionality can be deployed by virtualization of core network functions and customized to specific requirements using the technique of network slicing. Mobile edge applications for mission-critical and machine-type communications, which are run as virtual machines, as well as the mobile edge platform, which provides mobile edge services, can share the same network function virtualization platform. We propose a new mobile edge service called Multiparty Communication Control. The service provides open access to multi-party call control for mobile edge applications. Using the service interfaces, a mobile edge application may place a call that is multi-party with desired quality of service, make to join or to leave given participant, fetch information regarding the ongoing communications. The figure illustrates a typical message flow of mobile edge application initiated multi-party call with call participants management. As a part of service specification, we build the data model and provide interface definition. The multi-party session and session participants are all presented as RESTful resources. The resources are manipulated using HTTP methods post, get, update, and delete. To initiate a new multi-party multimedia session, a mobile edge application sends a post request to the multi-party session resource. It provides the session description, maximal number of session participants, maximal session duration, application and request identifiers. The information about existing multi-party session includes session start time, active time, the session order, and participant number. Adding a participant to existing multi-party session involves creation of application function session with quality of service in the network. For each participant, the application provides media information. To summarize, the container resources support get method, which retrieves a list of all its child resources, and post method, which creates a new child resource. The leave resources, in addition to the get method, support also patch method, which updates the existing resource, and delete method, which deletes an existing resource. To assess the visibility of the proposed interfaces, we model the visions of the network and mobile edge application on the state of a multi-party multimedia session. The network and mobile edge applications must have synchronized visions, and the multi-party multimedia session state models must expose equivalent behavior. The figure in left shows the simplified multi-party session state model as seen from the network point of view, and the figure in right shows the simplified multi-party session state model as seen from a mobile edge application. Both models are formally described, and it is proved that they expose equivalent behavior using the concept of weak bisimulation. One of the key performance indicators of mobile edge computing is latency, which should be defined on per service basis. The latency is evaluated for API requests for session creation and for API requests for participant managing. The time budget for local task execution can be calculated as a product of data size in bits and computational workload in CPU cycles per bit over the CPU frequency. The time required for message composition and processing for both the request and response are under 2 milliseconds. In addition to theoretically evaluated latency, an experiment for API functionality is conducted. The experiment includes pushing a batch of 100,000 operations, post requests for multi-party session creation, and the respective 200 OK responses. The configuration experiment setup includes a client running on a host equipped with Intel processor of 7th generation, running at 3.4 GHz with 8 cores and 8 GB of RAM. The server is running on Intel same generation at 2.6 GHz with 6 cores and 16 GB of RAM. The server is implemented using Vertex, which supports a REST-based interface toward the client, and Redis configured to work in single node without clustering. The figure in left depicts a decimated portion of operations latencies where the initial part is clearly different with respect of the following, and the effect is based on the so-called warm phase. Should this effect have to be taken into consideration when a service level agreement is prepared, then it has to be described separately, but the rest of the results presented are about the part of so-called steady state. The figure in right depicts the steady state of latency as an ingredient of service level agreement, and the focus is set on the worst case part as a limiting factor for the latency budget of the service. About 99.5% of all requests have under millisecond latency, but part of the rest may hit even 30 milliseconds. This is specific for both cases of the experiment, with a single serving instance at the endpoint and with 4 instances. The figure in left depicts the half millisecond part of the latency population in steady state, as it constitutes over 95% of all recorded post-trials. By increasing the number of instances from 1 to 4, it becomes clear that while keeping almost the same shape of the probability density function of latency moves to lower values as whole. The figure in right depicts the Gaussian mixture model of the steady-state latency in the case of 4 serving instances. Here the aim of the modeling part has at least 3 purposes. First, to reduce the amount of data stored for simulation and development purposes. That is, it is much more practical to generate expected latency from a 5-component model rather than keeping in cache 100,000 samples. Second, to help in service level agreement formulation for the latency as a key performance indicator. Third, to help key performance indicator monitoring for eventual slow shift towards higher values of latency. The open access to multi-party call control at the network edge may be beneficial for mission-critical scenarios and Internet of Things healthcare use cases. It enables creation, modification, and termination of a multi-party multimedia session by applications adding and removing multi-party session participants dynamically, as well as management of media streams used. The proposed API for multi-party call control enables dedicated third-party applications to react promptly on situations requiring management of multi-party sessions with specific quality of service and saves the backhaul network resources. Thank you for your kind attention.
Okay, thank you very much, Evelina. A very nice presentation. I think it was very appropriate for these times of pandemic to have this information about multi-party calls, which we are all very much used now all these days. So is there any question from the audience? Any questions so far? Okay, and is there anything from the internet, from YouTube channel? Any question? Okay, so just as we have 1 minute, I have just fast question for you, Evelina. More related to my ignorance from this topic. It is in some of the figures you showed us, you were depicting the latency versus I don't know which was the other variable, but it was, I don't know if it was related to the number of people included in the multi-party call. Is it, do you include this topic in the analysis? I mean, how many people is in the multi-party call, or it is only assuming that all of them have more or less the same flux of information and all of them are using the same bandwidth?
Okay, thank you for the question. We just simulate the latency of the request and response for adding a participant. No matter how many participants are involved in the session. We just evaluate the latency because it is one of the basic KPI of mobile edge computing technology.
I see. Okay. Okay, thank you very much. So if there is no more questions, okay, then we will go for the next presentation. Thank you, Evelina. So next one is Evaldas Stankevicius. Evaldas Stankevicius from Lithuania. Yes, hello, how are you? The audio, please.
Good morning. Thank you for the floor.
Good morning, Evaldas. So you can share now your screen.
Thank you.
This presentation is going to be, title is Telecommunication System and Aeronautical Telemetry System in the 1429, 1518 MHz frequency band. And as I told before, you have around 12 minutes for the presentation and a couple of minutes for the questions. Okay, so thank you very much, Evaldas. When you want, you can start.
Okay, thank you very much for the presentation. So as the chairman presented, I will share our results, our study regarding the cross-border coordination between two systems. And it is the International Mobile Telecommunication System. So simply talking is the mobile networks, and the Aeronautical Telemetry System in the 4029, 1518 MHz frequency band. So we, together with my colleagues, Sarunas Oberauskas from Communication Regulatory Authority, Vidas Kalesinskas from Vilnius University, and Mindaugas Zilinskas from Vilnius University and Communication Regulatory Authority, and me as a co-author and the presenter, a member of the Vilnius Gediminas Technical University. So the first of all, introduction, why such studies are needed, why such studies are important, and what's the main key points to present here. So first of all, we made a study in co-channel compatibility between two mentioned systems in the 1.5 gigahertz frequency band. It is important because this frequency band is quite qualified regarding the radio propagation conditions for the fourth generation, fifth generation mobile networks. That's why in this frequency bands we have also working other systems as aeronautical networks, radio relay networks, broadcasting networks, and other let's say, possible systems. But all frequency bands are allocated and used by some systems. And if we would like to change the allocation, for example, for mobile networks, we need to perform the electromagnetic compatibility studies in order to prove that this frequency band is feasible for the mobile networks, and it's possible to have such a systems in a particular frequency band. So the main key novelty we found and evaluated during our work. So first of all, it is more practical rather than academical, because we currently we have, let's say, the protection criteria and coordination distances from telemetry systems. It means that those systems, those radio receivers in particular countries are saved by particular protection criteria. But we see that possibly those criteria are overprotecting the systems. It means that we do not use the frequency in most effective way possible. So we investigated the new possible approaches in this area, how to perform the electromagnetic compatibility in order to share the frequencies as much as possible. So we proposed two possible protection criteria to use. It is I over N, interference over noise, and plus C over I plus N. Is the carrier frequencies, carrier signal strength over the interference plus noise. So those criteria are more precise, more appropriate, because, for example, if you have at least the sensitivity of telemetry system, the ATS system, you can use at least I over N criteria. And if you have the, let's say, the permitted, the acceptable minimum levels of receivable signal strength of ATS receiver, you can use the C over I plus N. And each case is different. So if the neighboring countries have different approaches, means that if one country would like to use the mobile networks and the other country would like to develop the telemetry systems or other systems, you need to case by case calculate the electromagnetic compatibility. And in the current situation, that is, let's say this, the calculations and the interference criteria might be overprotective, so it should be well adjusted or improved. And this, for example, these two possible new approaches could be used in general manner between all the neighbor countries, at least in Europe or worldwide. So with the use of more precise interference criteria, we could achieve much better frequency sharing between the countries and inside a country, not to overprotect, let's say, every radio system, not only, let's say, mobile networks or the ATS systems. So this frequency band, as I mentioned, it is important not because we just found some frequency band where something is changing, but this frequency band is important also for the fifth generation mobile networks as an additional frequency band. So that's why the mobile operators in Europe and worldwide will deploy the 5G networks and currently deploying the 5G networks in the countries. And when you present the new technology, you need to have the new frequency bands. So 1.5 frequency, 1.5 gigahertz frequency band could be like an additional part of spectrum for every mobile operator to ensure the requirements from their clients and communication authorities. So electromagnetic compatibility simply can be done or performed in two ways. It is sharing studies when the systems use the same frequency band. So it means that we have limited frequency band and systems would like to share it. And compatibility studies, it means when the systems operate in different frequency bands. So in our study, we were more focused on core channel because the frequency band is quite narrow. So one country can use it for mobile networks, another country can use for the ATS, broadcasting, and other fixed systems. So how to share the frequency on the, let's say, between the countries on the border when the, let's say, the between the transmitter and receiver in both countries are very close distance. So evaluating the probability of interference, as I presented the interference criteria we used. So we created the hypothetical networks of 1.5 gigahertz and hypothetical networks of ATS systems, telemetry systems. So it is the telemetry system. So it is it has the transmitter and some receiver at the ground and the plane flying around the receiver and performing the activities and sending and receiving the signals. So in those two hypothetical networks, we always calculate the so-called DRSSS. It means the desired received signal strength. This in general, it is like a C, carrier, received signal, the wanted signal, and the other plane, the IRSS, the interference received signal strength. This is the interference from the interfering system from the neighboring country. And in each case, regarding the density of mobile networks, regarding the format, the configuration of ATS systems, you will have different calculation, different results. And regarding the interference criteria, if, for example, it is possibly overprotective, so it means that one country which would like to deploy the mobile networks would need to have a large separation distances to ensure the protection of ATS system. But we raised the question, maybe it is not needed, maybe it is overprotected. So we calculated the situation with the hypothetical networks. So we created a hypothetical networks, first of all in Lithuania, and then additional calculation were made also in Poland. And we modeled the situation when the ATS system is working in a Kaliningrad area. So it's very narrow territory, just a couple of tens of kilometers. So the possible interference from mobile networks from neighboring country could be investigated and could have influence to ATS receivers. So that's why we use such a close situation. So the parameters we use, we try to find as much let's say precise parameters that would be the systems that is working in reality. So to model the system with the practical real parameters. So the parameters of the ATS transmitter on board, means on the plane, which are flying in some area, at the height of 2,000 meters and 10,000 meters. And somewhere there is an ATS receiver with the particular thermal noise, sensitivity levels to calculate the possible interference. And international mobile systems, or the so-called simply the mobile networks, we also created like three base stations, cluster of base stations with the default parameters, with default emission powers. And calculated the interference level at the ATS receiver point. So if two ways of calculation were done. So first of all, when you only know the ATS receiver's sensitivity, it is the minus 35.0 98, and then you can calculate more precisely if you know the signal, minimum signal strength that it is needed for the ATS receiver from the ATS transmitter. So you can use the C over I plus N and calculate how much, let's say, power budget do you have in order to accumulate the noise level and interference level from the mobile networks from neighbor country. So the hypothetical network looked like in the picture. We have the cluster of base stations. We have the ATS transmitter at the height of 2,000 and 10,000 meters, and the ATS receiver with the antenna height in the neighbor country. Two possible antenna types were used in ATS system, because it's not so, let's say, not so much public information about the ATS system, how it is working, because the system is developed many years ago and it's not so much information. So in the ITU radio communications standards and recommendations, we found two different antenna types that could be used. It is so-called the radar type and tracking type antenna. Next slide, I will show the antenna patterns, how it looked like. And the simulations are made, first of all, with one cell, 3 sectors of base stations, and then the cluster with 57 57 sectors. And as I mentioned, 2 different antenna heights of ATS transmitter. So these 2 antenna patterns used for the ATS system, according to 2 different ITU radio communication recommendations. So in the right side, we see the tracking type antenna. It is more like narrow beam, which tracks the plane on the horizon. And then radar type antenna system, it has more wider antenna pattern. Also, it is a wider pattern for the, let's say, for the tracking of the system in the horizon, but also it could take more interference in much wider angle. So, and the calculation itself. First of all, if the, let's say, ATS transmitter is flying around the ATS receiver, the angle between this system and according to the antenna pattern, the gain is changing also. So it's highly dependable situation and the outcome of the situation, how the ATS transmitter and receiver is let's say set, or what is the possible area where the ATS on board the transmitter can fly around the receiver. So it is.
Evaldas, sorry, you have 1 minute more. Okay.
Yeah. Okay. No problem. So it's just the situation regarding the, let's say, the gain and elevation angle. And 2 different calculations were made. First of all, with antenna pattern according to the ITU recommendation 1459. So the both pictures show that results highly depend on the aircraft altitude. So using IN method, it can be seen that the coexistence is possible when the aircraft is flying at 10,000 meters altitude. And however, the aircraft altitude is of 2,000 meters, the protection criteria is always exceeded. And if we use the more precise, the more correct interference criteria of C over I plus N, we see that there is a margin of 35 dBs regarding this protection interference criteria. So we have really high power budget, which means that ATS system is overprotected. The same calculations with different antenna pattern regarding the ITU recommendation of 1851. So we achieved or we get the same outcome, that that is more precise C over I plus N interference criteria shows that there is a power margin of minimum 17 dBs. So we see that in radio communications that the 17 between 17 and 35 dBs of power margin, it would let us to share the spectrum much more, let's say, in much more effective way. So the main outcome, the main result of this study, that if we would use the more precise, the more correct approaches with the more precise interference criteria, we can achieve the possible positive interference margin between 17 and 35 dBs. And in who, let's say, working in the radio communication area knows that it is a beneficial major change in electromagnetic compatibility. And the second conclusion, that if we use the C/R interference criteria, you can achieve the better electromagnetic compatibility comparing with the I/R. And the third general conclusion, that if the countries would let or would change the approaches using the more precise interference criteria, the radio systems would develop much, let's say, in much beneficial way, and both countries would have more developed radio systems as it could, because if the system is overprotective, so it stops the other radio systems development in a particular country and for the neighboring countries. Okay, thank you for your attention.
Okay, thank you very much, Evaldas. Is there any fast question? Because we are running out of time for this part. Okay, so then maybe we can save it for, if something arises, maybe we can save it for the end of the session, because I think we are getting out of time. Okay, so thank you very much, Evaldas. Sorry, we don't have time for questions.
No, thank you. Thank you very much.
Okay. So next presentation is going to be modeling a leaf and spine topology for VM migration in fog computing, and it's going to be presented by Pedro Juan Roch from Spain. Pedro, again, you have around 12 minutes for presentation and a couple of minutes for questions. Okay, so when you want, you can share the presentation. Thank you. Oh. Pedro, no se te oye. Your micro. No, we cannot hear you.
There we go.
Yes, now.
Okay, sorry. So thanks very much, Mr. Chairman. My name is Pedro Juan Roch. I'm coming from Spain, from Universidad Miguel Hernández. And this presentation is about modeling a leaf and spine topology for VM migration in fog computing. First of all, we'll talk about a small introduction.
Sorry, Pedro. Could you please switch the full screen of the...
Oh, sure. Sorry.
No problem.
Sorry, what's going on here?
Down.
Oh, sorry. There we go. Now?
Yes.
Is that okay now? Oh, sorry for the inconvenience. So let's start again. My name is Pedro Juan Roch. I'm coming from Spain, and this presentation is about modeling a leaf and spine topology for VM migration in fog computing. First of all, we'll make a small introduction. Then we'll talk about leaf and spine. Next, we'll present the modeling of leaf and spine, and finally, we'll draw some conclusions. Well, IoT mobility in fog computing environments. Here we have associated VMs may try to follow IoT devices as close as possible, minimizing both latency and bandwidth use. VM migration among hosts within fog facilities is the solution, and the optimal path is given by the data center topology. The target here in this paper is getting an algebraic model for a leaf and spine architecture to be applied to the VM migration in a fog computing environment. So end devices may move around, so their VM migrate. Well, as an IoT device moves away from the coverage area host 1, just like here, and it gets close enough to host 2, like here, VM migration takes place. So VM migration, VM number 3 just moves from host 1 to host 2. Well, let's start with FAT3, right? FAT3 is a typical in traditional data center facilities. Here we have 3 layers of switches, just like 1, 2, and 3, and just another extra layer of hosts, right? And the layout is heavily dependent on parameter K, such as the number of switches on each layer and their connections, and the number of hosts in the topology and their connections. Here we have an example of a FAT3 topology for K equals 4 and oversubscription rate 1:1, right? But in modern data center facilities, we need the following features. We need equal distance among hosts without any blocking link, thus increasing throughput performances and lowering latency. We also need use of COTS, commercial off-the-shelf switches, meaning less power consumption and lower cost. And we also need that topology is based on east-to-west traffic, leading to scale-out networks, thus adding independent resources to the network so as to enhance performance, as opposed to north-to-south traffic, leading to scale-up networks, thus adding new resources to the network so as to enhance performance. So the proper solution here is leaf and spine, right? So leaf and spine is typical in modern data center facilities where we have just 2 layers of switches, the lower layer called leaf and the upper layer called spine. And here each leaf switch has to connect to all spine switches in a just full mesh topology fashion, right? And here the number of leaf switches is equal to the number of downlink ports per spine, given by variable P. And the number of spine switches equals the number of uplink ports per leaf, given by variable K, right? And here we have an example of a full mesh topology between all leaves and all spine switches. Well, benefits of leaf and spine. All hosts are at most 2 hops away from each other, meaning that just 1 hop away if they both share the same leaf switch, or otherwise 2 hops away. But here we have a drawback, which is when the number of hosts is very high, many leaf switches are needed, so there might not be enough ports in spine switches. And in such cases, 3-layer designs prevail. Well, let's go for the modeling leaf and spine building blocks. First, we have the spine switches. We have Q switches going from 0 to Q minus 1, counting from left to right. And each spine switch have lower ports going from 0 to P minus 1, going also left to right? Then we have leaf switches. We have P leaf switches going from 0 to P minus 1 from left to right. And in each leaf switch, we have Q upper ports going from 0 to Q minus 1, and we have W lower ports going from 0 to W minus 1, right? And we also going to model the hosts, and we have PW minus 1 hosts. Sorry, we have PW hosts going from 0 to PW minus 1, and each host has just 1 unique port, meaning the 0 port. All right, so we're going to present the modeling of each of those building blocks, right? Starting for the host modeling, at host layer, it only matters what happens to source A and destination B, and the rest of the hosts do not take part in communication, so they are useless in this context, right? So for the source host, it sends a message, right? H sub A sends the message, and destination host, it receives the message, right? H sub B receives the message. So generalizing, meaning putting all hosts in a concurrent manner. So we have all hosts going from 0 to PW minus 1. They only just send and receive or receive the message. Regarding the leaf modeling, this is the logic. If a message is received from a lower port, right, it is forwarded towards destination host if hanging on the same leaf switch, or otherwise it is sent upwards. And if a message is received from an upper port, it is forwarded towards destination host, right? So generalizing, meaning putting all leaf switches in a concurrent manner. Here we have the algebraic expression for all leaf switches coming or going from 0 to p-1, where in this point we have the condition, meaning that if source switch and if a source host and the destination host share the same leaf switch, it performs this action, otherwise it performs the other action, right? And talking about spine modeling, if a message is received from any port, right, it is forwarded towards destination leaf switch through the direct link between them, as we have full mesh topology, right? So generalizing, meaning putting all spine switches in a concurrent manner. Here we have for all spine switches going from 0 to q-1, all received messages are forwarded all the way to the destination leaf switch. And the final model is obtained by putting in parallel all three previous models conforming a leaf and spine architecture, right? So putting all three different entities we just modeled, right? Hosts, leaves, and spines, right? And as seen at every layer, communication only takes place in all redundant paths existing between source and destination. Therefore, by applying linear superposition, the model is behaving according to the leaf and spine specification. So the model is verified. Finally, conclusions. An algebraic model has been designed layer by layer in order to show the VM migration redundant paths among any two given hosts. So it meets the leaf and spine specifications and it behaves according to expectations. Eventually, this model may permit to obtain all available redundant paths between one source host and one destination host. Also, the chain of devices composing each of the paths, and also the ports used in each device, right? So this model permits to obtain all the features of any given path. So this is it. This is the end, and thanks very much for your attention. And if you have any question, just ask.
Okay, thank you very much, Pedro. Thank you for being in time. I pretty much appreciate. Is there any questions from the audience here? Okay, any question from the internet?
And from me also, Professor Rodríguez.
Oh, sure.
No
problem.
Professor Rodríguez, I have a question.
Yes, please proceed. Yes, thank you.
Thank you. Pedro, you simulate, you design just the architecture, not the trigger for virtual machine migration. Is that okay?
Yeah, that's it. I mean, we just perform a theoretical work. And the theoretical work says that if an IoT device just moves close enough to another antenna, to another facility, just the via migration takes place. Why does it take place? We didn't design the trigger, as you said, right? The trigger must be maybe the RSSI of the antenna received. Maybe when it's closer from let's say antenna 2 than antenna 1, the via migration takes place, or it even might be because of the load balancing policies, maybe. So we just leave this for a future work, and we just modeled at this point the mechanism of migration, not the reason of the migration.
Okay, thank you.
Maybe for a future work, this might be a good point.
Okay, thank you very much, Pedro, and thank you for the questions.
You're welcome.
Okay, if there are no more questions, nothing from YouTube. Then, okay, thank you very much again, Pedro.
You're welcome.
We move for the next presentation. Next one is presented by Svitlana Matsenko from Latvia, and title is Development of the Fibonacci Octal Error Detection Code for Telecommunication Systems. So, Svitlana, you have the micro, so as you want, you can start. Please remember 12 minutes for presentation, okay?
Hello. Good morning. My name is Evelina. I'm from Riga, Latvia.
Svilana, sorry, there is a lot of echo in your audio. Can you switch off maybe your speakers?
Okay. Now. Okay. I'm sorry.
There's still a lot of echo.
Now, okay.
Maybe you should switch off your speakers.
And now. Yes. No.
Echo is very persistent.
Yes. No.
No, I'm afraid it's not very good.
I'm sorry. Okay. Today I present my research idea.
Sorry. It is very difficult to understand you. There is a lot of echo and the quality of the audio is very bad. Could you please check the system?
I don't know what's like. No.
Can you try again?
And no. I'm sorry. I didn't know like that.
Sí, dígame.
Yes.
Sí, dígame.
No, maybe we can move to the next presentation while you try to fix it.
Okay.
Okay. If new, is it okay for you?
Okay. Yes. Okay, and no.
New, are you ready for a presentation?
Yes.
Yes. So okay. So I think it is better Svitlana if we let New do his presentation, and then we try again later with you. Okay.
Yes.
Okay. Thank you. So please, Svitlana, can you block your screen?
Mở camera lên. Bên kia tắt thì mình mới show.
Okay, can you stop sharing the presentation, Svitlana?
Stop sharing. I don't share in.
Okay, this is it.
Okay.
Okay, so then we're going to move till we wait if Svitlana is able to fix the problem. So next one is going to be presented by New Hong from Vietnam. Presentation is called Enabling Wireless Power Transfer and Multiple Antenna Selection from IoT Network Relying NOMA. So New, when you want, you have 12 minutes. Thank you.
I would like introduce. My name is Nguyễn Hồng Nhu. I'm living and working in Vietnam. I would like to share idea my paper with title Enabling Wireless Power Transfer and Multiple Antenna Selection to IoT Network Relying NOMA. Content, motivation. introduction, system model, outage performance, NOMA and OMA. Numerical results, conclusion. Abbreviation, NOMA, IoT, SIG, OMA, WBC, OB. Motivation, the fast growth of IoT applications. Result, requirement of heterogeneous IoT sensor asset. Sensor access into networks in the upcoming 5G network. These applications are related to capability of device in D2D network and M2M network, other circuits and application associated with IoT systems. An animal of power is consumed by these small sensors and IoT device to serve their data transmission and communication. Introduction. The energy harvesting technique is robust to tackle this problem by harvesting the energy from the surrounding environments. Specifically, signal is recorded firstly for the user with the best channel condition, while assuming all the user signal at interference. Motivated by these papers, we formulate the problem of selection of beacon and antenna selection to evaluate outage performance of true NOMA user. In this model, Figure 1 show the IoT system containing the AB asset board, relay to user and beacon. From the system model, we set up the algorithm equation with two signals X1 and X2. After the clock X1 as relay, the corresponding SI and R is expressed by equation. Continue. The clock is to which SIG is employed to eliminate interference. The SI and R to the clock is given by here equation here. Similar to the receiver and the clock signal at destination, we have general equation. Next, the destination is required to record H1 at T1 at below with equation. the SI and R to record H1 at D2 is given by with equation here. After 6, the SI and R to record H2 is given by equation. The best channel is selected with the index of antenna equipped at the AB at formulate. Okay. From the system model, we can see beacon will transfer energy to relay. We can compute harvested energy at relay with equation E, and the transmit power level of the relay E with VR. We had calculation outage performance analysis NOMA. Outage analysis at D1 with OB1. We have outage at D2 with perfect 6. The law form expression is computed to provide outage analysis at D2 at in perfect 6 KS with OP2. The calculation steps for an OMA K are the same as for NOMA, and K of asymptotic calculation read on the paper. We have outage probability destination be expressed at with equation O, OP, I, OMA. In this session, we saw the comparison of IoT system relay outage performance up to user using NOMA and OMA. These users are grouped in downlink of the AB using NOMA and OMA. The user are grouped in downlink. I'm sorry. Their user are grouped in downlink of the AB using the relay fading channel under different simulated parameters. We can see with the tree and one antenna K with NOMA and three and one antenna with OMA. In figure, compare outage performance comparison of D1, D2 of NOMA and OMA with energy power beacon by noise by variant K equal 1 and K equal 3. Next, outage performance comparison of D1, D2 for NOMA and reset energy power base station noise by variant with with energy with the factor power distribution. Let's continue figure 5 outage performance comparison of D1, D2 of NOMA and OMA reset with the energy power beacon noise by variant the factor power distribution. Conclusion. In this paper, we had investigated the IoT system by enabling energy harvesting and transmit antenna selection schemes. The relay scheme with wireless power transfer technique benefit to such IoT with performance improvement for too far use who need assistance of wireless power transfer assisted relay. We derive implicit form for the outage probability for two distant user in the considered IoT system. Thank you for your attention.
Okay, thank you very much. Thank you very much, Mr. New. Is there any fast, quick question? Because we are getting to the end of the gap of this session. Any question from the audience? Is there any question from YouTube, from the internet? Okay, so as we have only 10 minutes to finish this session, I'm going to try again with thank you very much. No, we don't have more time for questions. Thank you very much. Very nice presentation.
Yes.
Thank you. So next we're going to try to connect with Svetlana. Svetlana, are you there?
No, bị mình thoát rồi.
Svetlana, we have lost Svetlana. So maybe she's trying to fix the technical problems. Let's give her a couple of minutes. Darius, are you there? I'm going to try to connect with chat with Svetlana. It's not here. Okay. Well, meanwhile, if you have anything to share, any questions about any of the presentations, if you're still there, we can take the time now to waiting for Svetlana. But I am afraid she's not getting back.
Thank you for perfect sharing.
I have done my best. First time I'm sharing online presentations. So I think it's first time probably for everybody. Not first time Zoom video conference, but probably first time presentations. So you have done a very good work. Thank you very much. Thank you all for coming to the conference, and also thank you Darius and Aldimantas for your for the organization. And I hope next year we would have time to meet in person in Palanga. Okay, I know all of you, all presenters and organizers have done a very deep work, a lot of effort to have everything ready for the presentation. Okay. So, oh, Svetlana, we have Svetlana here. Hello, Svetlana. Can you hear us? I can see your screen, but I cannot see you. You there? No. She's missing again. Okay. Svetlana, are you there? Let's give her a couple of minutes. She's trying again. No, it's not working. Okay. We can see that you are trying to share your screen, but we cannot see the presentation, neither you. Hello? Hi, Svetlana, can you switch your video or audio on? Because I'm not sure if you can hear me. I'm afraid you cannot. Okay, so let's wait for a couple of minutes more. This session, remember, it finishes at 10:30. So I'm afraid we will not be able to continue because at 11 we have another session. But for me, there is no problem if Svetlana is here, we can wait for her. But not sure. Oh, hi, Darius. Can you hear me? Hi, Darius. We are having problems with one of the presenters, Svetlana. We had a problem with Svetlana. She had problems with the audio, and we have lost her. So this is the only presentation remaining, but we are not sure if she's coming back because.
She is coming.
Okay, there we are. Hi. One of the presenters.
Hello, hi. No? Do you hear?
Yes. Now, don't worry.
I'm so sorry. No. My presentation. One minute. I'm so sorry. one minute. Okay.
Yeah, there we go. Okay.
Okay.
Thank you, Lana. So I'm going to present you again fast. There we go with Svetlana Matsenko from Latvia. She's presenting development of the Fibonacci octal error detection code for telecommunication systems. Please use 10 to 12 minutes, okay? And then we give a couple of minutes for questions. Thank you.
Okay. I'm so sorry. And today I presented my presentation, our idea, and this is a development of the Fibonacci octal error detection code for telecommunication systems. Today, telecommunication systems use a large number of different codes. This is cycling codes, this is polar codes for 5G, this is LDPC codes, and we're using error detection codes. This is another class of coding. Some of the error control codes, for example, cycling codes such as Reed-Solomon, BCH, which have high noise immunity, require complex methods of encoding and decoding code combinations. As a result, the implementations of these methods in information transfer system leads to an increase in their cost and decrease in reliability and speed. In addition, most encoding and decoding devices, as a rule, don't process the property of cell control. Therefore, it is difficult to implement end-to-end control of information on the basis, covering both this processing and transmission using the same code. Such control makes it possible to reduce hardware cost and increase the speed of exciting telecommunication systems. However, the exciting codes designed to transmit information don't process the property of E2E control. In this work, for the E2E control of telecommunication systems, the Fibonacci octal is used in minimal form, which has a simple structure and a very high error detection ability. And the important task necessary for telecommunication system using the Fibonacci code is the ability to convert it to binary code for communications with binary digital system, and vice versa, the ability to convert binary codes to the Fibonacci code. To convert data, we propose use Fibonacci octal code, which consists of a sequence of 4-bit codes models containing 8 Fibonacci number. And important features of the Fibonacci octal code is those code combination. All these moduli are relatively easy to convert to the number of 3 bits binary modulus and vice versa. And research object, the idea of this works, this is convert data using Fibonacci octal code, convert data binary to Fibonacci, Fibonacci to binary, because many devices using binary code. Also, however, there is another type of code, this code, another type of redundant coding, in which coders use the natural redundancy, already exciting its structure. Because if we're using this type of coding device based on this coding, more speed and simply than if we're using cycling code maybe and another type of coding. The natural redundancy of such codes requires less hardware to implement encoding device, as it has already been partially implementation in device that generates code word of the basic task. Also methods and decoding device based on code switch nature redundancy also have a simple structure. And this slide shows coding in a minimal form of representation. This is a Fibonacci code, and you can see Fibonacci numbers. This is Fibonacci code in minimal representation, and some structure of this code, which weights, which code lengths, and another information. All devices, all the above mentions noise resistant codes, which nature redundancy, including Fibonacci code or binary code. This is code with nature redundancy, or permutation. These codes can a common drawback, it requires a conversion operation from the Fibonacci codes to binary codes, and vice versa for binary codes to Fibonacci codes to communicate with binary techniques. Now you can see information about the fraction of detectable errors in digital device based on the minimal form of the Fibonacci codes. You can see some information, and this code has some high error detection ability, and this is 99.9% with code length equal 32. This is high error detection ability of this code. And we propose some method for convert data using error detection code based on the Fibonacci octal code for convert data from binary to Fibonacci and from Fibonacci to binary code. And this method consists of some steps. The first, the binary code multiply of 3 is divided into modules consisting of 3 bits, starting from LSB bit and leading to the MSB bit. The result will be a binary octal code. If the total number of bits is not a multiply of 3, then zeros are added to the left of the MSB, so that the total number of digits in the binary number becomes the multiply 3. Each binary model is converted to the corresponding model of the Fibonacci codes. And the next step, the Fibonacci octal code is formed from Fibonacci modules and the proposed for conversion binary code to the Fibonacci octal code and ends. And we proposed the methods for converting Fibonacci code, octal code to binary code. And this method consists of 4 steps. The Fibonacci octal code multiply of 4 is divided into modules consisting of 4 bits, starting from 0 LSB and leading to the MSB bit. The result will be a binary octal code. Is not multiply of 4, then zeros are added to the left of MSB, so that the total number of digits in the Fibonacci octal code become the multiply of 4. Each Fibonacci model is converted to the corresponding model of the binary code. The Fibonacci is formed from binary model, and the process for converting a Fibonacci to binary codes ends. This is some algorithm methods for conversion. This is code using Fibonacci octal system. This is some example how these methods using. If we have some binary number, and this table shows some information about octal type and Fibonacci type and how convert this system. Of course, we can use this system in the telecommunications system, and also we can use this code in for building for synthesis of the component of digital device. And now you can see some counters in factory, and maybe another type. This is counters, and this is some information about how using this code in the structure of digital device. And now you can see high-speed Fibonacci counter with parallel work. This is information collection in transmission system with counter, and this is the same counter. And this counter use Fibonacci code, and this counter using this code and consists of the sum structure. This is control unit number 1. This is unit of disposition, analyzed unit, register. This is flip-flop structure, and counter 0 setting unit. And this is digital device using end-to-end control system, because using error detection code and works in error detection code. And the next slide shows some information. This is modeling on this counter, which you using this type of coding, and you can see some information about how this counter works using error detection codes. This counter based on the minimal form of the Fibonacci codes and using in these codes. And of course, idea of this work. This is some Fibonacci octal codes, and these codes help this device convert information to binary form and Fibonacci form, and vice versa. Okay, and this is conclusion. We proposed methods for converting binary octal codes to the binary octal codes and vice versa. And this is methods using some information, some modular structure with 3-bit binary code and 4 bits Fibonacci code. And this is research about data converting information from binary to Fibonacci octal code and for Fibonacci to binary octal code. Okay, this is it. Thank you very much. Thank you for attention. I'm so sorry for...
No problem. It happens.
Yeah.
I'm afraid we all have to get used to this. I'm sorry, and thank you very much. I'm afraid we don't have time for questions because we still have one presentation. I almost forgot it. I'm sorry because of this mess. So last one is going to be from Elans Rats from Latvia. It is entitled Supervised Machine Learning-Based Classification of Video Traffic Types. So please, Svetlana, if you could stop sharing.
Okay.
Darius, are we on time?
I think,
but
well, I think 10 minutes, it will be enough.
Okay.
Should be enough. Okay.
Okay, you heard Elans, 10 minutes.
Okay, thank you. I'll try to be as
brief
as possible.
Thank you.
I'm a postdoctoral from Latvia, and I'm working on machine learning applied for network traffic in scope of my postdoctoral project. And so first, I'd like to share some motivation why I'm doing this. The idea is very simple. We are going to use an SDN network, which controls network, yes, to perform some resources allocation and control for different types of traffic. But we need some decision-making element because different types of traffic have different requirements. For some traffic, it is better to provide higher bandwidth. For other traffic, latencies. Sorry, what is going on? Can you see my screen, or somebody else is trying to share?
No, we can't see you.
You can't see me, yes?
I think that maybe they are trying for the next session.
It seems, because Dejan Dragic has started screen sharing.
Yeah, and he's for session 7. So
I see.
Dejan, If you could please stop the presentation.
I wrote a message, okay, to next session people who are waiting, and they will stop share as soon as they can.
Thank you.
There we go.
I see. So we can continue, yes. And so we use two different types of traffic, video traffic. We used live video stream traffic, and we used recorded playback of the very same video fragment. For both of these video fragments, we have used Twitch platform, which allows saving live stream videos in archive.
No? Yeah.
Garsą įsijunkite.
Sako, pirmą kartą man labas
Labas
rytas.
rytas.
Prašau, žodžiu, neturėjau.
Tai va, kai kopijuoji į naršyklę, tada nėra.
Ja, tai aš anksčiau visą laiką iš nuorodų, kai PVD yra nuorodai, turėjo normaliai, taip nekeisti. Jau čia kažkas su Zoom. Ne taip.
Okay.
Pirmą kartą susidariau, dabar pradėjau jau nervuotis ir šitą mikrofoną.
So we have captured the traffic using Wireshark and exported it into CSV format.
Ankstesnė sesija ne visai sklandžiai vyko, nes elektra trūkinėjo, dinginėjo, tai...
For processing via MATLAB. So...
Pas pirmininką. Tai jo toks biškai buvo...
Darius, please silence the audio.
As a classifying parameter, we have used the intensity of traffic packets, which showed to be quite good parameter, but other parameters can be used in future as well, so software can be improved. And for network traffic, there is such thing as it collects every packet from every connection, and we need to perform filtering by using, for example, source IP address to select only packets relevant to the stream. Here you can see in picture the traffic nature for on-demand video traffic, which is a record. Similar picture have been obtained for live stream video as well. You can here see both of these traffic types. Yellow is on-demand video, which is transmitted in short bursts with high intensity, and live streaming video has lower intensity, but it is present constantly. So we need to try and classify traffic based on this intensity by using different supervised machine learning algorithms. First, and the most important thing, is to select appropriate window size for segmentation of this traffic. And here, the most natural choice, obvious at the beginning, is to use the time interval between bursts of the on-demand video traffic. However, this is quite a high number of time, which is 10 seconds, which is a lot. So we try to reduce this window size. And I will go straight to the results by using four most popular algorithms for video traffic captured at 1080p 60 video quality mode with 10 seconds window size, both for raw data and filtered data, which means that this data, for example, raw data, has been split into two subsets, which is training data and testing data, which was used to estimate the accuracy. And the same has been performed for filtered data. As we can see here, mainly all these algorithms can predict, or should I say better, classify traffic type quite accurately, except for naive Bayes classifier, which shows poor results for raw data, which is unfiltered data with different packets from other connections. The same results have been obtained for other video quality modes, and there is additional one more thing. that we have tried to be more realistic about it. So we can use cleaned, filtered data to train machine learning algorithms. However, if we expect this algorithm or model to work in real time, it will have to deal with real and raw unfiltered traffic. So we have modeled such situation when we have training data clean and testing data real, and there is a problem of time delay. So in order for this algorithm to work precisely, it is necessary to eliminate this time delay between expected, should I say, pattern, which is being searched in traffic, and real traffic windows. So basically, we have 10 seconds video traffic. For blue signal, you can see the burst is at the very beginning of the window. For red traffic, the burst is in the middle. So this leads to quite poor accuracy. And this time invariance is the cause of this. If we perform a 5-second, introduce 5-second delay for the field raw traffic, red traffic, so we shift it by 5 seconds to the beginning, the accuracy is once again improved, except for naive Bayes model, which, as it has been shown, deals poorly with noisy data. So we go straight to the conclusions, and direct use of traffic intensity samples is possible. This yields acceptable results for many algorithms, except for naive Bayes. Neural networks have been used as well, for example. But this requires strict time alignment of data for this to work, which is in real situation, should I say, unrealistic, yes? So future work consists on using statistical parameters of traffic intensity rather than traffic intensity samples themselves. Accuracy evaluation for versus different parameters such as window size. We change different window size, we change intensity sampling time, as well as we try to create hybrid methods which would perform initial processing with unsupervised methods with further improvement of accuracy by using supervised methods. This is continuing work on my project. So thank you, and sorry that it was so
thank
unorganized.
No, sorry for us. No, it was technical problems that have been keeping delaying all the presentations. I'm really sorry, because we don't have any time more for questions. So if there is anybody interested, maybe they can do it by email later, because we have to give the gap for the next session, I'm afraid. No, Darius?
Yes, exactly.
Okay, so thank you very much, everybody. I'm sorry for the problems.
Thank you, Mr. Chairman.
I see you next time in person in Paraga. Thank you very much.
Thank you.